Hey guys, Mr. Backerwick here. In this video, we're going to look at end behavior models. Now, sometimes as we're looking at complicated functions, there's a way that we can use a simpler function to help us model the behavior of the graph. So for very large values of x, we can sometimes model the behavior of a complicated function using a similar one that's going to act in virtually the exact same way. So in this first example, we're going to look at a couple of functions, and we're going to look at what happens on the ends of the graph. So on the right-hand side for larger x values, and on the left-hand side for larger negative x values. So the two functions we're going to look at, we've got our f of x function, which is 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. And then for our g of x function, it's just going to be 3x to the fourth. And we're going to graph these out, and we're going to compare the graphs as our x values get larger to the right-hand side and larger to the left-hand side. So in my calculator, I have both of those functions typed in. I've got the f of x function typed in as my y1. I've got the g of x function typed in as my y2. I'm going to do zoom 6 to get my 10 by 10 window. And as we're looking at small x values, as we're looking at kind of a zoomed in picture of our graphs, they don't look very similar at all. But what we want to do is we want to kind of zoom out on these because we're focusing more so on what's happening on the ends of our graph versus what's happening in the middle. So I'm going to go to my window, and I'm going to change my window. For my x minimum, I'm going to make that go to negative 20. For my x maximum, I'm going to make that go to positive 20. And for my y max, I'm going to make that go to 500,000. In our functions, we've got things being raised to the fourth power. So if we think about exponential growth, these are going to start to grow very quickly. So I want some really big y values so that I can look at these graphs. Now, as I hit graph, what we notice is that our graphs, since we have kind of this zoomed out look to it, they're almost overlapping. So that more complicated f of x function, we can model the end behavior of that by just using that simpler g of x function. Now, there is a way that we can tell if a function is a good end behavior model using limits. So the function g is a right end behavior model for our function f if the limit of the ratio f of x over g of x as x is approaching infinity, if that limit is equal to 1. Now, there's also a left end behavior model. So the function g is a left end behavior model for the function f if that limit as x approaches negative infinity of that same ratio f of x over g of x, if that limit is also equal to 1. So if we revisit that previous example with our f of x and g of x functions, if we look at the limit of the ratio f of x divided by g of x as x is approaching positive infinity and negative infinity, we'll check what that limit ends up being to see if this g of x function truly is a good end behavior model for our f of x function. And I'm going to graph this out. So in my calculator, in the y1, I have that ratio f of x on the top of my fraction over my g of x function on the bottom. I'm going to do zoom 6 to get my nice 10 by 10 window. Now I'm looking at the limit as x approaches positive infinity and negative infinity. So as we go far out to the right-hand side, it looks like this graph is flattening out there around that y value of 1. So the limit as x approaches infinity is 1. And if we look on the left-hand side as we go to negative infinity, again, it looks like this graph is flattening out around that y value of 1. So we can say that the limit as x approaches negative infinity is also 1. So because this limit as x approaches infinity was equal to 1, then g of x is a good right end behavior model. And similarly, because as we looked at the limit as x approaches negative infinity, that was also equal to 1. So g of x is also a good left end behavior model for our f of x function. So in general, when you're dealing with polynomial functions, a good way to build an end behavior model is by looking at the leading term of your polynomial function. So if you've got a function f of x equals a sub n times x to the nth plus a whole bunch of other stuff, if that's the leading term, the thing with the highest powered x on it, that leading term is going to have the greatest impact on the end behavior of your graph. So the simpler version, the g of x version of that, is just that exact same leading term. So like we saw in the previous example, for the f of x function, the leading term was the 3x to the fourth. So that's what we used as our g of x function to be the n behavior model. Now, if you're looking at rational functions, things can get a little bit more complicated. So here in this first example, we've got the function f of x equals 2x to the fifth plus x to the fourth minus x squared plus 1 all over 3x squared minus 5x plus 7. If you want to find a good n behavior model for a rational function, if your numerator and denominator are each polynomials, then what we can do is use what we just talked about to work on building our n behavior model. So I'm trying to build a g of x n behavior model using what I know about these individual polynomial functions in the numerator and in the denominator. So as we're looking at the numerator, the leading term, the thing with the highest powered x on it, is that 2x to the fifth. So 2x to the fifth is going to be a good n behavior model for the numerator. And if we wanted to find a good n behavior model for the denominator, the leading term there is that 3x squared. So those two pieces together are going to have the biggest impact on the n behavior of our graph. Now we can simplify this down. 2 divided by 3 doesn't really simplify down, so I'm just going to leave that as 2/3. But then if I take x to the fifth and divide it by x squared, I'm going to get x cubed. So this g of x function, since it was built by looking at the n behavior of the numerator and the denominator separately and then just reducing that down, this g of x function, where it's 2/3 x to the third, is going to be a good n behavior model for that original, more complicated rational function. Now, as we're looking at this second example, we've got 2x cubed minus x squared plus x minus 1 all over 5x cubed plus x squared plus x minus 5. And we're going to do the same thing. Now, I guess this function was already called g of x, so I'm going to call my n behavior function, I'm going to call that h of x. So if I look at the leading term on top, that's going to be 2x cubed. And if I look at the leading term on bottom, that's going to be 5x cubed. Now, if we look at reducing this down, those x cubes are just going to cancel each other out. So we end up with an n behavior model of 2/5, which is just going to be a flat horizontal line along that y value of 2/5. And the reason that's happening, the reason why there is not a variable left on here, this graph actually has a horizontal asymptote at 2/5. So as we look far out on the right-hand side and far out on the left-hand side, it flattens out around that 2/5 value, which is why 2/5 is a good n behavior model. The function in part A does not have any horizontal asymptotes, which is why its n behavior model was a polynomial function instead of just a flat horizontal line through a specific y value. That's going to be it for this video. Thanks for watching.